picture this. It is a Tuesday night. You are maybe a couple of months, maybe a year or so into your 3D printing journey.
Right. You are past the absolute beginner stuff.
Exactly.
Yeah.
You have successfully navigated that notoriously steep learning curve. You know what a proper first layer squish is actually supposed to look like.
Essential knowledge.
Oh, absolutely. And you have got your standard PLA profiles dialed in perfectly. You have, even wrestled your PTG settings into submission.
Fighting off the stringing and all that.
Yeah, the stringing, the bed adhesion issues, all of it. So you are feeling pretty confident about your setup. And because of that, you decide to load up a massive 12-hour print.
Oh boy, the big one.
The big one. It is a complex, multi-part assembly, or maybe, I don't know, a highly detailed architectural model. So you watch the first layer go down, and it looks absolutely pristine. It is laying down like glass.
Best feeling in the world.
It really is.
Yeah.
So you go to sleep, or you go to work fully expecting to come back to this beautiful, finished object. But instead, you walk up to your printer, and an hour, 11 and a half disaster has struck.
The classic 3D printing heartbreak.
Utter heartbreak. The print failed right at the very end. You are just standing there looking at like a catastrophic layer shift, or a part that has just snapped clean off its supports.
Or the dreaded massive blob of plastic doom covering the nozzle.
Yes, the blob of doom. And naturally, your first instinct is to blame the machine.
Well, of course, everybody does.
Right. You think, well, my bed leveling has somehow drifted, or my belts just magically lost their tension overnight.
Or the Z offset changed itself while you were out of the room.
Exactly. Or, even worse, you blame yourself and you spend hours and hours tweaking retraction settings in your slicer. So, okay, let's unpack this.
Let us unpack it, yeah.
Because the absolute truth of the matter is, the success or the failure of your print is very often determined long before your printer's nozzle even begins to heat up.
It really is.
It ultimately comes down to two vital sources: the physical spool of plastic you decided to buy and the digital file you decided to download. I mean, we spend so much time obsessing over the hardware.
We really do.
But the raw materials we feed that hardware dictate everything.
That is exactly right. And that actually sets the perfect stage for what we are doing today. Our mission for this deep dive is to synthesize the insights from two incredibly comprehensive guides.
Two really dense pieces of source material.
Yes. One of these guides focuses entirely on a detailed technical comparison of the major filament brands out there, and the other one breaks down the top 3D model libraries available to us today.
Right.
By bringing these two perspectives together, we are going to build a next-level decision framework for you. The overarching goal here is simple, but it is critical. We want you to be able to evaluate the source.
Both the physical material and the digital data.
Exactly. Before you ever hit that print button.
And just to set the baseline here for everyone listening, we know you already understand the basics of PLA and PTG. You know how to clear a clog. You know how to clean your build plate.
We are not starting from zero.
Right. We are talking about the ecosystem level of decision-making today. So we are going to start with the most modern approach to 3D printing right now, which is full ecosystem integration.
The walled gardens versus the open ecosystems.
Yes. Specifically, we are comparing Bambu Lab and Prusa across both the physical plastic realm and the digital file realm.
It makes a lot of sense to begin with the physical side. Specifically looking at Bambu Lab filaments. Bambu Lab entered the filament market as a very logical extension of their X1 and P1 printer ecosystem.
Right.
When they launched, they really shook up the market with high-speed Core XY machines, but they quickly realized that, high speed requires highly predictable material flow.
You cannot print fast with unpredictable plastic.
Exactly. So the filament is primarily aimed at their own users. I mean, you can certainly use it on other machines if you manually configure the temperatures and flow rates.
Sure.
But the key feature, the thing that sets it apart in this specific ecosystem context, is an RFID chip. It is integrated directly into the plastic core of the spool.
Okay, let us talk about that RFID chip. Because that chip fundamentally changes the daily workflow. I mean, it sounds like a small detail.
But it is not.
No, in practice, it is a massive shift in how you interact with your machine.
It absolutely does change everything about the workflow. When you place that spool into their AMS, which is their automatic material system,
right,
the machine reads the RFID chip wirelessly. It just automatically configures the material type, the exact color, and the recommended hode end and bed temperatures.
That is so wild.
It is. You do not have to manually select anything in the slicer or on the machine's touchscreen. It completely removes a significant point of user error.
Which is huge.
I mean, think about how many times you have accidentally sliced a model for PLA, but you actually had PTG loaded in the printer.
Oh, I've done that more times than I care to admit.
Right. And the temperatures are wrong, the cooling fan speeds are wrong, and the print just fails immediately. The RFID system prevents that. And, we actually have specific numbers on the cost of this convenience.
Let's hear the numbers.
Bambu Lab PLA Basic costs 549 to 649 CZK per kilogram. This puts it, firmly in the middle of the pack price-wise.
Okay, so it is not incredibly expensive.
No, it is not. And they also offer a refill system, which is just the wound plastic without the central core.
Oh, that's smart.
Yeah, that reduces the price by roughly 80 to 120 CZK, which is a nice touch for reducing plastic waste and, saving a bit of money if you are willing to load the master spool yourself.
Okay, wait. I have to push back a little bit here.
Yeah.
Based on what we constantly see in the community discussions, is it not true that most filaments in this specific mid-tier price range come from the exact same handful of giant chemical factories?
Yeah.
I mean, if I buy a spool of basic PLA from Bambu Lab, am I really getting a magical, highly engineered plastic formula? Or is it basically the exact same raw material I could buy from a competitor?
That is a very fair point.
Why should I pay an extra 100 CZK per spool just so the printer can do something I can do in 3 seconds on my slicer? Is this actually worth it, or is this just like an Apple-style tax for 3D printers?
That is a very fair challenge. And actually, the discussions on the official Bambu Lab forums openly acknowledge exactly what you're saying. Most standard filaments in this mid-tier price range do indeed come from a select few massive factories in Asia.
Right, I'm figured.
They differ primarily in their packaging, their school design, and of course their marketing. If you were to do a blind scientific test of Bambu Lab PLA Basic, testing its tensile strength and its thermal properties, it would perform very closely to other PLAs from similar origins. So no, it is not a completely unique magical plastic formula.
So what are you actually paying for then?
The Bambu magic, the real reason you are paying that specific price of 549 to 649 CZK, is strictly in the RFID integration and their internal quality control.
Oh, okay. Quality control.
Yes. They test a larger percentage of their spools to ensure the dimensional accuracy works flawlessly with their specific high-speed slicer profiles. When a machine is throwing the print head around at 500 millimeters per second.
Which is incredibly fast.
It is. A slight dip in filament diameter can cause instant under-extrusion at those speeds.
Okay, so you are not paying for better chemistry. You are paying for the friction removal and the absolute guarantee that the software matches the hardware.
Precisely. You are buying time and reliability. Now, we have to contrast this closed-loop approach with Prusament.
The Prusa alternative.
Right. Prusament is the in-house brand of Prusa Research, and it is manufactured right in Prague. Their marketing and their entire value proposition rests on something completely different than an RFID chip.
What is their angle?
It rests on absolute, verifiable quality control transparency.
And they do not just promise it is good on a glossy spec sheet. They actually prove it to you.
Exactly. They offer a unique online quality control protocol for every single spool they manufacture.
That is pretty cool.
It is very cool. Every individual spool has a unique QR code plastered right on the side. You can scan that code with your phone and look up the inspection protocol online.
What does that actually show you?
It will show you a graph of the exact diameter, the ovality, and the weight along the entire length of that specific spool of plastic you are literally holding in your hands.
Okay, let us pause on the word ovality for a second.
Yeah.
Because that is a term intermediate users might not fully grasp right away.
Sure.
I mean, we all know about filament diameter. We know it should be 1.75 millimeters. But why does ovality actually matter?
That is a great question. So ovality refers to how perfectly round the cross-section of the filament is. If a filament is manufactured poorly, it might be 1.75 millimeters wide on the x-axis, but maybe 1.65 millimeters wide on the y-axis.
Right, so it's literally an oval.
Exactly. It becomes an oval, and when that oval filament hits your extruder gears, the gears grip it inconsistently. The tension fluctuates.
Oh, I see.
This leads to microstuttering as the plastic is pushed into the hot end, which then translates to visible, repeating artifacts on the surface of your final print.
Like weird layer lines.
Yes. Prusament guarantees a tolerance of plus or minus 0.02 millimeters for their PLA, which is incredibly strict, and they guarantee it stays perfectly round. This level of extreme traceability ensures that you know exactly what you are putting into your machine.
It is a completely different philosophy of quality. I mean, one is about digital convenience, and the other is about industrial precision.
Very well put.
But let us bridge this physical discussion over to the digital side. Because you can have the most perfectly round, dimensionally stable filament in the world, but if your digital file is garbage, your print will be garbage.
Absolute garbage, yes.
If your filament is the raw clay, the database you download your model from is your canvas.
Yeah.
And if we are talking about Bambu Lab's physical ecosystem, you really have to talk about their digital one. That brings us to MakerWorld.
Yes, MakerWorld. It is the youngest of the major databases we are looking at. MakerWorld was launched by Bambu Lab in 2023.
Pretty recently.
Very recently. But in a very short amount of time, it has established itself as a massive player in the space. And it did this specifically because of how it integrates perfectly with Bambu Studio, which is their desktop slicer, and the Bambu Andy mobile app.
And that deep integration relies almost entirely on the 0.3 MLF file format, right? Like this is a huge shift away from the old standard.
Correct. On MakerWorld, designers upload what the platform calls print profiles. These are complete 0.3 MLF project files. This is a very crucial distinction for intermediate users to understand.
Okay, break it down for us.
An old STL file is just raw geometry. It is a dumb mesh of triangles. It has no concept of what a 3D printer actually is. It does not know what a layer height is. It does not know what support material is. And it certainly does not know what color it should be. A 0.3 MLF file from MakerWorld, on the other hand, contains all of that information.
It is all baked in.
Exactly. It holds the precise settings for the layer heights, the specific painted support blockers, the specialized infill patterns, and crucially, the color separations.
Which is huge for the AMS.
Massive. If you have an AMS unit, you download the .3MF, and it is entirely ready to go. The system knows exactly which extruder to use for which specific triangle on the model.
Wow.
For Bambu users, it means absolutely zero tuning before printing. You just hit print on your phone, and the machine wakes up and handles the rest.
Okay, look, that sounds like a total utopia. But there's a very critical question we need to raise here about MakerWorld's underlying economy.
Oh, the point system.
Yes, the point system.
Yeah.
They introduced a system that rewards designers with actual gift cards for the number of downloads and successful prints their models get. Now, on one hand, that is fantastic because it attracts professional creators who deserve to be compensated. But on the other hand, it creates a very weird incentive structure.
It really does.
Does this not just flood the platform with low-effort clones, like people taking an existing popular model, tweaking the scale by 1%, and re-uploading it just to farm points and get free filament?
That is exactly the downside, and it is a major friction point in the community right now. The financial incentive of the point system has led to a noticeable influx of models that are, well, more or less clones, or very minor, lazy modifications of existing projects from other platforms.
Which makes searching a nightmare.
It can make searching for original, high-quality, complex models a bit frustrating at times, because you have to wade through a sea of incredibly basic keychains and duplicate articulated dragons.
Ugh, the articulated dragons.
They are everywhere. This is where we need to counter with Printables, which is the platform operated by Prusa Research.
Printables has a very different vibe. It feels much more curated.
It does. Printables has established itself over the last few years as one of the highest quality databases on the market. Just like MakerWorld integrates with Bambu, Printables has deep integration with Prusaslicer.
Okay.
There is a literal print button on the website. You click it, and it automatically opens Prusaslicer on your desktop with the file loaded and a pre-filled printer profile.
That is super convenient.
It is, but its truly superior feature, and how it actively combats the clone problem you just mentioned, is its review system of Make Photos.
Oh, the Make Photos are brilliant. They are infinitely more valuable than just a 5-star text review.
They are completely essential for verifying a model. When someone prints a model from Printables, they do not just leave a comment saying looks good. They can upload a high-resolution photo of their actual finished print.
Proof that it works.
Exactly. And they tag the specific filament brand they used and the specific printer model they used. This ensures that you, as the next user coming along, know a model is actually physically printable before you waste 50 grams of your expensive Prusament.
Right, because nobody wants to waste filament.
Nobody. You can see real-world proof that the aggressive overhangs actually work without failing. You can verify that the mechanical tolerances for hinges or snap fits are correct. You know, the designer did not just upload a broken file, they modeled in Blender without ever testing it in reality.
That is a huge relief.
And they also have active moderation and very popular theme-based monthly contests. This keeps the community actively producing fresh, original content tailored to specific engineering or design challenges, rather than just farming points with clones.
So let us synthesize this into our decision guide for this first section. If you want a frictionless appliance-like experience, match your ecosystem.
Match it, yes.
Bambu users should absolutely stick to MakerWorld and Bambu Filament or their refill spools to get the maximum benefit out of that AMS and the high-speed material profiles.
Agreed.
Prusa users are going to get the smoothest, most reliable ride by sticking with Printables and utilizing Prusament with those perfectly tuned, factory-tested profiles in PrusaSlicer.
But, here is the flaw in that entire walled garden philosophy. It assumes you want to be locked in.
Very true.
What if you are running a highly modified Voron that you built yourself? Or a neutral Anycubic or Creality machine? You cannot rely on an RFID chip to save you?
No, you cannot.
You have to rely on raw chemical consistency. And that naturally shifts our conversation to the independent powerhouses and the historical archives of 3D printing.
Right. So let us talk about Polymaker. They are fascinating because they do not make printers at all.
Not at all.
They just make filament. Their entire business model relies on making plastic that works well on everybody else's hardware.
Yes. Polymaker is a large Chinese manufacturer that positions itself specifically as the premium, globally available independent choice. They have a massive, highly specialized portfolio.
They got a lot of options.
They really do. They have the PolyLite line for standard, reliable materials like PLA and PTG. They have PolyTerra for matte, aesthetically pleasing, eco-friendly options.
PolyTerra looks great.
It prints beautifully. They have PolyMax for massively improved mechanical properties and impact resistance. And they have extensive engineering lines like carbon fiber infused nylon and polycarbonate. But their main strength, the thread that connects all these diverse materials, is absolute consistency.
And we actually have a very specific number to illustrate that consistency. Polymaker PolyLite PLA hits a strict declared diameter tolerance of plus or minus 0.03 millimeters.
That is a very tight tolerance.
It is.
Yeah.
Now, I have to ask you to explain this mechanically. As an intermediate hobbyist who is mostly printing, desk organizers, board game inserts, and the occasional structural bracket.
Yeah.
Does a 0.03 millimeter tolerance actually matter? Or is that just marketing fluff that looks really good on a spec sheet to justify a higher price?
What's fascinating here is how that microscopic tolerance translates directly to the physical mechanics and the fluid dynamics inside your hotend.
Okay, let us nerd out for a minute.
Let us break down what is actually happening. Your slicer calculates exactly how much plastic to push through the nozzle based on a hard-coded assumption.
Right.
It assumes that the filament entering the extruder is exactly 1.75 millimeters thick. It uses that exact assumption to calculate the volume of the cylinder of plastic.
Okay.
If you have a cheap budget filament that fluctuates wildly from, say, 1.70 to 1.80 millimeters over the span of a few meters, the actual volume of plastic entering the melt zone changes constantly.
So the math breaks down.
Exactly. The math breaks down entirely. The slicer asks for 10 cubic millimeters of plastic, but the extruder gear pushes 15 because the filament got thicker in that spot.
Oh, wow.
This results in irregular extrusion. You will see sudden pressure spikes in the nozzle, the plastic bulges out, you will see visible, ugly banding on your vertical walls.
And that ruins the print.
It does, and more importantly, your parts will not fit together. If you're printing a print-in-place hinge, that sudden over-extrusion will fuse the joint solid.
So it is entirely about controlling volumetric flow.
Yes, volumetric flow is everything. A consistent diameter means consistent extrusion. If you are printing functional mechanical parts, a tight tolerance prevents that irregular extrusion and ensures strict dimensional stability.
Which is crucial.
Incredibly important, especially with their highly rated PolyLite PTG. PolyLite PTG ranks among the most recommended options for functional parts exactly because of this.
Right, because PTG is structural.
When you are printing structural components where minimal warping and precise dimensional accuracy determine whether the part is usable or if it goes straight into the trash, you need that plus or minus 0.03 millimeter guarantee.
That makes perfect sense.
Yeah.
The hardware is only as accurate as the assumptions the software makes about the material.
Exactly.
Now, let us look at the independent digital database. Downloading a raw STL file from Thingiverse is like buying a piece of flat-pack furniture without the instruction manual or the pre-drilled holes.
That is a harsh but very accurate metaphor.
You have the raw material, but the geometry alone does not tell your printer how to actually build it.
No, it does not. Thingiverse is the oldest and largest database out there, and it comes with all the structural problems of being the oldest. Thingiverse has been operated by MakerBot since 2008.
2008, that is ancient in 3D printing years.
It is. We have to remember what 3D printing looked like in 2008. It was the absolute wild west of the reprap movement. Because it has been around for so long, it contains millions upon millions of models.
It is basically a historical archive.
It is an incredible historical archive. If you have a highly specific problem, there is probably a solution for it buried somewhere on Thingiverse.
But age brings a massive amount of historical baggage.
It does, and I have to seriously warn users about this historical baggage. The database suffers from a staggering number of models that were created 10 or 15 years ago.
Right.
These models are completely untested on modern high-speed machines. You will frequently encounter what we call non-manifold geometry.
Okay, explain non-manifold geometry for us. Why does it break modern slicers?
Sure. A manifold object is, quote-unquote, watertight. If you filled the digital 3D model with virtual water, none would leak out.
Okay, I can picture that.
Non-manifold geometry means there are literal holes in the digital skin. The 3D modeling software used back in 2010 might have allowed a designer to intersect two shapes without properly merging their digital boundaries.
Oh, so it looks fine on the screen.
It looks fine to the eye, yes. But when you pull a non-manifold STL into a modern slicer, the slicer's math engine panics. It cannot distinguish the inside of the object from the outside.
Oh, no.
It might generate random solid blocks, or it might just skip entire layers, leaving your physical print incredibly fragile.
That sounds like a nightmare.
It can be. Furthermore, you might download a raw STL file that lacks critical text details about print orientation, recommended materials, or specific infill percentages required for strength.
Because back then, people just assumed you knew how to figure it out.
Exactly. Add to that an interface that feels very outdated, a search function that is notoriously slow, and pages full of intrusive ads. It can be a frustrating experience.
So what is our decision guide for these independent, non-ecosystem options?
Choose Polymaker when you are running neutral printers like an Anycubic or a Creality, and you need absolute consistency across a wide range of engineering materials without relying on a proprietary RFID chip.
Right.
If you use PrusaSlicer, which is a very popular open source software right now, it already contains an extensive library of highly tuned profiles for Polymaker filaments, making the initial setup very easy.
And what about the digital side?
As for the digital side, turn to Thingiverse exclusively when you are hunting for a highly specific niche replacement part.
Like what?
If you need a replacement battery cover for a remote control car from 2012, or a very specific adapter for a vintage telescope, it simply does not exist on newer platforms like Printables or MakerWorld.
Okay, that makes sense.
Thingiverse is indispensable for finding those specific historical niches, but it should not be your primary starting point for modern, complex projects.
Okay, high quality is great. We all love perfectly consistent plus or minus 0.03 millimeter filament and flawlessly documented 3MF project files.
Of course we do.
But let us face reality here. Makers print a lot of plastic. We go through kilograms of this stuff. We print giant Gracinity base plates. We print massive storage bins.
It's a lot of bins.
So many bins. We have to talk about the budget trade-offs and how saving money requires spending significantly more time verifying and managing your sources. Let us talk about Sunlu.
Yes, Sunlu targets primarily price-sensitive customer. Their entire business model is built around economies of scale. They want to offer filament at the lowest possible price point while keeping it at a theoretically usable quality.
Right.
And they cover all the common consumer needs. They manufacture PLA, PTG, ABS, and TPU.
And the appeal is absolutely massive because of the sheer price point.
Yeah.
When buying bundles of 4 to 10 spools directly from their website, the price of Sunlu PLA drops below 300 CZK per kilogram.
Which is wild.
That is less than half the price of the premium options from Bambu or Prusa we just discussed.
It is incredibly cheap. It allows you to tackle massive projects without breaking the bank.
But
But if we connect this to the bigger picture, we have to understand the physics of what you are sacrificing for that price. The primary trade-off for budget filament is batch-to-batch inconsistency.
Oh, okay.
The discussions in the community frequently report that while one spool of Sunlu Black PLA might print beautifully with flawless layer lines, the very next spool of black PLA from a different manufacturing batch might exhibit aggressive stringing or much worse layer adhesion.
So you are directly trading your money for your time.
Yes. You might save 300 CZK on the purchase, but it means you suddenly have to manage the material much more actively.
Give us an example.
Take PTG, for example. Budget PTG often sits in massive warehouses and absorbs moisture before it is even vacuum sealed. PTG is hygroscopic, meaning it acts like a sponge for humidity.
Right. It pulls water from the air.
When water gets trapped in the plastic and you feed it into a 240-degree hot end, that water instantly boils into steam. This process is called hydrolysis.
And that is bad.
Very bad. It creates microscopic explosions inside the melt zone. That is why budget PTG pops and hisses, and it completely ruins the chemical bonds between your layers.
Oh, wow.
With Sunlu, you frequently have to dry your PTG much more aggressively right out of the box. You will also have to spend time tweaking your slicer temperatures by 5 degrees here or there, or adjusting your flow rate to compensate for those diameter fluctuations we discussed earlier.
That sounds like a lot of work.
It is very telling that Sunlu actually sells very popular, affordable filament dryers. They know the necessity of drying budget materials.
This physical reality perfectly mirrors the digital side of budget or untested models. Just like budget filament requires constant tuning and active thermal management, raw STLs you pull from the depths of the internet require rigorous verification.
Oh, absolutely.
You cannot just blindly slice a file and hit print.
Absolutely not. You must develop a strict verification checklist before you commit to a long print. When you find a model, the very first thing you do is look at the comments section.
Always read the comments.
Read what other users actually experienced. Did they struggle with a specific overhang? Did the designer forget to account for shrinkage? Then check the make photos, assuming the platform supports them.
What are the massive blinking red flags we should look out for when verifying a digital file?
The most common and frustrating red flag is if a model is uploaded in inches instead of millimeters.
Oh, I hate that.
Most slicers operate entirely in metric. If you import an STL modeled in inches, it will look microscopic on your build plate.
A tiny little speck.
A tiny speck. You will have to manually scale it up by exactly 200 and 540%. And even when you do that, the complex mechanical tolerances for screws or bearings might be completely wrong due to conversion rounding.
What's another red flag?
Another massive red flag is if a complex model is split into dozens of poorly named files with absolutely no assembly instructions. If you download a file and it just says part 1 through part 40, run away.
Just walk away.
And the absolute most important red flag is if there are no successful prints shown by the community. If a model has been online for a year and no one else has managed to post a photo of it successfully printed, you probably will not be able to either. It is likely a digital render that defies gravity.
So our decision guide for the budget tier is this. Sunlu is the perfect choice for rapid prototyping for education, for messy kids projects, or for massive cosplay armor.
Yes, cosplay is a great use case.
If you are printing a giant Mandalorian helmet that you're going to be aggressively sanding, filling with Bondo, and painting anyway, you do not need a perfect glossy surface finish straight off the printer. Save your money and buy Sunlu in bulk.
Exactly. But for functional load-bearing parts where catastrophic failure is not an option, avoid it.
Okay.
Likewise, verify every single digital file. If a file lacks a clear open source license, or if it has absolutely no recommended print settings regarding wall loops or infill density in the description, proceed with extreme caution.
Good advice.
You might be wasting meters of filament and hours of machine time trying to guess the correct orientation or the necessary support structures.
Okay, let us pause this rapid-fire comparison for a moment. We have covered the premium closed ecosystems, the reliable independent powerhouses, and the necessary evils of the budget trade-offs.
You've covered a lot.
We really have. So I want to synthesize everything we have discussed about physics and software into one golden rule, one highly actionable piece of advice that you could take to your workbench today to stop those hour 11 failures.
I am ready.
Here's where it gets really interesting. We call this the baseline calibration rule.
I like that framing. The baseline calibration rule. It is essential for intermediate users who are starting to mix and match brands and platforms.
The rule is this. Whenever you introduce a new variable into your established setup, whether it is a brand new shrink-wrapped spool of budget Sunloop PLA,
Yeah.
or a highly complex, slightly questionable model you just unearthed from the archives of Thingiverse, do not just blindly start your massive 12-hour print.
Never do that.
You must print a standard 30-minute calibration model first. Use a simple Voron cube or the standard Bambu Lab calibration piece.
The reasoning behind this rule is pure risk mitigation. But you cannot just print the cube and look at it from a distance. You have to read the cube like a detective.
How do you read it?
That half-hour investment exposes batch fluctuations in the filament immediately. You take your calipers and measure the X, Y, and Z axes. If the cube is supposed to be 20 millimeters, but it is 20.2 millimeters on the X and Y, you know that specific spool is over-extruding, and you need to drop your flow multiplier.
And you can read the surface quality to adjust advanced slicer settings, right?
Exactly. Shine a harsh waking light across the surface of the cube. If you see the corners bulging out, your pressure advance, or linear advance depending on your firmware, is wrong for the specific viscosity of that budget filament.
Remind us what pressure advance is again.
Pressure advance compensates for the springiness of melted plastic in the hot end. A cheap, gooey PTG requires a very different pressure advance value than a stiff, premium Polymaker PLA.
Oh, that makes sense.
You inspect the sharp corners for stringing. You identify all of these microscopic problems on a 3-gram, 30-minute print before they cascade and ruin a 12-hour, 200-gram print.
It is entirely about establishing a known mathematical baseline before you commit resources. And we have to combine this physical calibration rule with a strict digital rule.
Yes. The digital counterpart to this rule is to always download the 0.3 MF file instead of the raw.stl file whenever it is available on the platform.
As we discussed with MakerWorld and Printables.
Right. The 0.3 MF format allows you to start with the designer's intended logic. You get their customized layer heights, their specific support blocker placements, and their intended part orientation.
It's just so much smarter.
And STL is just a mathematically dumb mesh of triangles. A 0.3 MF is a complete, intelligent project file. By starting with the .3MF, you eliminate the guesswork.
Right.
You ensure you are evaluating the model exactly as the creator intended, rather than trying to reinvent the wheel in your own slicer.
That is the ultimate takeaway here. Verify the physical plastic with a calibration print and a set of calipers. And verify the digital data by using modern file formats and checking community reviews.
Before we wrap up, I want to leave you with a final thought to ponder. Throughout this entire discussion, we have treated the physical filament and the digital files as two separate sources that you have to manually manage and verify.
Yeah, that has been the whole framework.
But think about how the lines between digital software and physical plastic are blurring at an incredible rate right now. Consider the Bambu ecosystem we discussed at the very beginning.
Oh, the RFID stuff.
Yes. When a multi-layered, highly complex 0.3 MF file downloaded from MakerWorld interacts with your slicer, and that slicer sends a digital command to an RFID-chipped spool of filament telling the physical plastic exactly how to behave, what temperature to melt at, and when to retract. You are experiencing something profound. You are no longer just a hobbyist melting plastic in a garage.
Would argue then.
You are managing an automated micromanufacturing node right in your own home. The software and the material are communicating directly to ensure a successful outcome. It fundamentally changes the nature of making.
That is a wild perspective, and it really shows where the technology is heading. We are moving from blind extrusion to intelligent manufacturing. We have covered a massive amount of ground today, from the fluid dynamics of consistent extrusion to the historical archives of MakerBot. For the full numbers, see printera3d.com.